Hello. So this is half of the binomial theorem lesson. We're actually going to skip over the binomial theorem in its entirety. For now, at least. We'll probably come back to it. But I want you looking at worksheet 7b in your packet, which is probably the very first set of notes we see. We'll come back to the binomial theorem of expansion later, maybe, if time allows. But in your notes, 7b, we're going to talk about binomial probability. Alright, so I think your notes start off right here. The idea is when we have a binomial probability distribution, we are looking at probabilities where there's two outcomes, either you succeed or you fail. And we'll see some very easy to understand examples coming up here. That's what I like about the probability section is oftentimes the problems are very, the context of the problems are very relatable, even if they're sometimes a little lame. So here, this problem that we're going to see in a moment is about a golfer. Will he get it onto the fairway or not? So that would be an example of a binomial probability distribution. There's a very exciting formula here that's given to you. And what I would like you to do in your notes is to write down what all these variables represent. So, let me move my... Sorry for the scrubby look I got going on today. It's the first day of spring break, so I thought I'd come to work, you know. I had to get ahead of my work, right? So, some variables that you need to define. N represents the number of trials. Wow. Okay, see if I can write today. N represents the number of trials. X represents the number of successes, whatever that is for the problem. What other variable shows up? Oh, P, that is the probability of success. And then there's something they define as Q, which is the probability of failure. And they might not tell you the probability of failure because these are complements to each other. So if they don't outright tell you Q, Q is just 1 minus P. For example, if probability of success is 40%, the probability of failure is 60%. So, I think we got them all. Yep. So if I go back to that formula, that is a very exciting way to calculate binomial probability for one particular number of successes. We're going to be using our graphing calculator, and we're going to use the probability PDF distribution. If you have taken a stats course, or you will in the near future, you're going to find out that there's two options, and we'll see it in a moment. There's binomial PDF and binomial CDF. CDF refers to cumulative probability distribution, where they add up everything that falls below it on the distribution curve. We're not going to be using that in PreCalc because we're just given like the most basic run-through of probability distributions right now. And actually, this formula here, it's not great, I'm going to be honest. There's a combination, and then it's multiplied by the probability of success to the number of successes, times the probability of failure to the number of failures. That's what n minus x would be. I'll show you how to do the first one by hand, and that's the last time I'm going to do one of these by hand. Now, if you don't have a graphing calculator that does probability distributions, that's a bit of a bummer. You're going to have to set these up, and I guess if you really were in a jam, you'd have to calculate the combination using the old combination formula with those factorials, you know, n minus r factorial. I don't even know what it is off the top of my head. It's how long it's been since I've used it. All right, so let's talk about this golfer. So the golfer has a probability of success of 0.7. So P is 0.7, which means the probability of failure is 0.3. So again, I'm doing this one the long way. He wants to know what's the probability that he's going to get it onto the fairway 14 out of the 18 times. So 14 is the number of successes, that would be X, and then 18 is the number of trials, that would be N. So using our little formula here, it would be out of 18 trials, so we're going to take combinations of 14, and we're going to multiply that by the probability of success, which is 0.7, to the X power, so to 14 times he's going to succeed, times probability of failure, which is 0.3, and then he would fail, let's see, 4 times, right? 18 minus 4 is 4. So, then I would have to go type this in my calculator, which I will do the long way this one time, and then I'm never going to do this again. I mean, it's not like the worst thing we've done, guys. It's just, if technology has advanced to the point where we don't have to do this, then like why? And that's one of the big fights I have with collegiate level, is if you're not using the formula, oops, I don't want to go there. If you're not using the formula for extending and like solving within the formula, and you're not doing really cool problems, then like stop wasting everyone's time by making kids do them with the old formula. Either extend it or don't. That's my thought. Okay, soapbox. I'm getting away from it now. All right, 18 combinations of 14 successes. Get out of the combination before you hit, you don't really need multiplication if you use parentheses, but 0.7, I'm not going to use parentheses here, to the 14 times, right? 14th power. Get out of the exponent times 0.3, and they would fail 4 times, we said? Oh, oops. It must be spring break if I can't even type right. All right, enter. Maybe I shouldn't be working. So this comes out to this answer. So 16.8% probability that he's going to make it to the fairway 14 out of 18 times. Exactly 14 out of 18 times. Now, if we change the question and say like at least 14 times, that changes things. So we'd have to go find the probability of him hitting it 14 times, 15 times, 16 times, 17 times, and 18 times, and then add them all up. But that's not what they asked, thank goodness, because obviously that takes a little more work, and also people who know about stats, there's an easier way to do it than even that. What I'm going to show you is on your calculator. Now, I'm going to be using the newest operating system for the TI-84s, so I have the CEs in my classroom. But if you have one of the older gray models with the older operating system, I'm going to show you what you have to type in. So this is for the older models. You're going to go to the distribution menu, and then you're going to choose Binomial, and then make sure you pick PDF, okay? And it's going to open up a parenthesis, and then in the parenthesis, you have to be careful how you list these numbers out because it goes in a very, very particular order, okay? So it starts off with n number of trials, and then you'll have to put a comma, and then it'll ask you for the probability of success, and then you put a comma, and then you type in the number of successes that you're looking for specifically. So that's the order in which they appear. Now, for our newer calculators, this is just, I love when technology advances and makes your life easier, which is obviously happens all the time, right? On the newer operating systems, if you go to, I'm going to get this bigger. We don't need all those keystrokes, right? The distribution menu, it's like A, I think, yeah. So it's kind of in the middle, so it doesn't matter if you scroll up or down, but I need to choose Binomial PDF. Make sure it's the right one. The newer operating system specifically asks you for the pieces of information. So like back in my day, you know, as a student, I had to remember what order to type everything in, and clearly if you do it wrong, it'll either give you a syntax error or it'll just give you the wrong answer if you typed in the wrong problem. So 18 trials, probability of success for this dude was 0.7. And then we're looking for 14 successes, exactly. And then when it says paste, it's pasting this information into that old school formula. See, right there. Isn't that nice? So no more memorizing, which is so good for someone like me who can't memorize anything anymore. All right, so we get the same answer. Clearly, Binomial PDF is going to be easier. So get your hands on a TI-84, even an 83 will do it, I believe. Any TI graphing calculator will have the option for some probability distributions. The newer the model, the more cool features you see, though. All right, so from here on out, no more of that combination formula. I'm using Binomial PDF from here on out. So apologies if you're doing it the old school way. All right, on your notes. I don't know if this is a problem. Oh, yeah, it is on there. It's number 2 on your notes, though. So that's a little confusing. I think we renumbered because we redid the packet. I say we, but it's really my coworker who's awesome. All right, so the probability that a substitute teacher does get a job on Friday is 32%. So that's what they're calling the probability of success, because you want to get hired for a job if you're a substitute teacher. And the probability that the teacher will work, what is the probability that the teacher will work on 3 out of the next 4 Fridays? So the number of trials that we're running through is 4. So out of those 4 trials, they're wondering what's the probability of 3 successes. So x equals 3. So I'm going to grab my calculator. And you, instead of going to the distribution menu, you can actually just do second entry, or you could go back up into here and open it back up, and you can overtype from the old information, which this one's kind of annoying because everything's wrong. So, womp womp. Alright, 4 trials. We have to delete that because it overtypes. Was it 32%? Yeah. So again, watch the overtyping feature. It's 32, so maybe it would have been smarter just to pull up the stinking thing again. And then we have 3 successes exactly. 9% chance. Alright, so I don't know if that's what they're hoping for or not, but not a good chance. Alright, so for my older calculators, what you typed in is you did binomial PDF, and then you pulled up 4. Number of trials is 4. The probability of success is 0.32. And then out of those 4 trials, we're hoping for 3 successes in this problem. And we came up with, I should write down the answer, huh? So approximately 9%. Again, college textbooks, they really like these decimal answers. They didn't really specify, so it's whatever you feel like, frankly, at this point. Whatever works for the problem and whoever your audience is. If your audience is like a math teacher, like I probably prefer the decimal answer. If your audience is like a real normal human in the real world, no one wants to hear things like 0.12358. Like they want something a little more user friendly. All right, sports. On average, a player misses 3 free throws out of every 8 attempts. Well, that's a very negative Nancy way to say that they make 5 out of 8. So what I'm going to change that to is that the probability of success is 5 out of 8. And I can type it just like a fraction in my calculator, so I'm going to leave it like that. So if the player goes and shoots 5 free throws, so this is now our number of trials. I don't know why I keep switching colors like this, guys, sorry. What's the probability that he misses no more than 2 times? So the question they're having is they want to know the probability that he will, and since I phrased it as making free throws, I don't know why I did that. I just did. They want to know the probability of him missing no more than 2 times. So that means he can miss 2, which means he makes 3, right? And then also he would miss less than that. So miss 1, he makes 4. Well, what if he misses nothing? That means he makes 5. Okay? So this would be miss 2, miss 1, miss none. You could have kept it in terms of missing free throws, and in that case the probability of success would have been 3/8, but then you got to think about succeeding is missing, and that's really confusing to me. Alright, so on our calculators we're going to be pulling up the binomial PDF, and our number of trials is going to stay consistent. It's going to stay 5 for each of these, and then our probability of success is going to stay consistent. It's going to be 5/8. That's us making free throws this time. The thing that's going to change, though, is this last number. So, in this first example, you're going to want the 3 to go here. You're going to make 3 free throws, and I already did this. I'm just going to steal my numbers if you don't. Oh, but I didn't write them down. Okay. So the first time you type in a 3, and then I would use that overtype option where you pull up the entry again. Then you type a 4 here, and then you type a 5 here, and you get your 3 different decimals. And whatever they came out to be, I'd add them together, and I get approximately 0.72. So this basketball player has a 72% chance of missing 2 or fewer free throws when he shoots 5. Okay. Alright, so binomial probability is pretty cool, especially if you have a calculator. And remember, our newer operating system has the really cool feature where you don't even have to remember what order to type things in because it'll paste it into the order for you. So that's really awesome. Alright, so that's a lie, isn't it? Let me go grab another file. I'll be back in a split second. And I'm back. Alright, so these were literally cut and pasted onto your notes. Thank you, Mrs. Hoffbauer. These are some examples from your textbook that we're going to look at. They probably showed up in another worksheet or an assignment, but let's just go ahead and do them now for practice. We have Alfonso, and he's taking a test that contains 16 true-false questions. So true-false meaning equally likely guessing 50-50 shot, right? So how many possible sets of answers to these questions would have exactly 12 correct false answers? So, if we're just flat out guessing with no knowledge, this is like a 50-50 shot on this test for every single question, right? So the probability of success is a 0.5. The 16 questions is our number of trials. And then the x is going to change in each question. So like here x is 12 and here x is 8. So for part A, if we start by finding the binomial probability of all that information, so binomial PDF, and again, newer operating system, I don't have to do tons of work here. I'm just going to type in 16 trials, and then 0.5 for my probability of success, and then 12 for how many successes we're looking for, exactly 12 it said. And I'm going to get the probability of, it's roughly 0.028. Now that's the probability of that happening. The question itself, though, is from your textbook, and it says how many sets of answers. So what I'm going to do next is I'm going to multiply this by how many ways I could just flat out guess and bubble in my bubbles for this test, right? So you have true, false, true, false, true, false, true, false. You have 16 questions where you're making a 50-50 shot, right? So there's two ways you could answer each question. Let's look at it that way. So instead of doing like 2 times 2 times 2 times 2 to the 16, 16 times out, can I just write that as 2 to the 16th power? So that right there, this is how many ways we could answer the test. I should say how many ways we could bubble. Answer is probably a better way, but how many ways we could bubble in the test. So if I type this on my calculator, the 2 to the 16th power times this teeny tiny probability, then I get approximately, and I don't know if it's exact, if I keep the decimal or not, probably not, 1,820, what do they call them, sets. So if my teacher was like super cool and said, oh, by the way, you're going to have exactly 12 answers that are false on this test. Like that seems like a really cool clue, right? Well, if I don't really know the content, I have almost 2,000 ways that I could make that happen. So the chances of me getting them all correct, not great. All right, so how many possible sets are there this time for 8 correct true answers? So again, same setup here, binomial PDF. Oh, I missed a few letters there. Binomial PDF. This time it's still 16 trials, still 0.5 for the probability of success, and then the x is now an 8. So if I'm just calculating the probability of that happening, this is what I would type, and I would get I wrote 1964 down. I don't know why I willy-nilly choose to have various sig figs. And then same thing here, we're going to multiply it. Oh, yeah, please do drag that down. 2 to the 16th power. And when I type this on my calculator, I get, oh boy, 12,870 different sets of answers that we could come up with that have 8 true answers. Yikes. All right, so good luck. Everyone thinks multiple choice testing is so easy. I mean, there's a lot of perks, right? But I don't know about you, but I end up second guessing myself like constantly. All right, so we have a sales representative who's got a 1 in 5 chance of making a sale. So that's our probability of success. You can say it's 1 over 5, or you can call it 0.2. I'm going to go with 0.2 because I don't like fractions. All right, the probability that the representative makes no sales this week. So in this case, this is weird. The probability of success would be making 0.2, but the number of successes would be 0 successes because they're not making any sales, right? And they have 12 appointments. So in your binomial PDF, you have 12 trials, you have a 0.2 chance of making any success, and what's the probability of having no successes? So I already typed that in, and I'm going to tell you it comes out to 0.0687, so 6.9% roughly. Alright, so what's the probability? Same sales rep has exactly 3 sales. So same setup, guys. The only difference here is instead of x equals 0, now it's x equals 3. So this is now a 3, which means I got 0.2362. And then this final question, they're going to make 10 sales. Keep dreaming, guy. It's not going to happen. Because when you do the probability, and again, you change this last number for successes to 10 successes out of 12, it's not great. It goes 0.000004, which is 0.0004%. If you want to change it to that. So really, really, really slim chance of this person making 10 sales. Which makes sense if you think about it, right? Because you only have a 20% chance of making any sale on any given, or making a sale on an appointment. So dream big. All right, so we're going to stop our binomial probability lesson there. We're going to take everything that we're kind of smushing into our learning for this week of distributions. We're going to chunk them into little bits. So there's binomial.